I was standing at the edge of this huge land canyon not long ago, and, just looking down into it, you feel so small. The power it must have taken to carve that out is, well, it's just humbling.
It really is.
But what if you took that same feeling, that same colossal scale, and dropped it miles under the ocean? That's what we're talking about today, submarine canyons.
Right. And our whole understanding of them is basically being rewritten right now.
So what's the big news? What's the mission for this deep dive?
The big news is a real shakeup. A German research team did this huge global analysis over 2,000 canyons and found that the old textbook idea that these are just river valleys that continue underwater is wrong.
Wait, so they're not primarily formed by rivers?
Not primarily, no. It turns out the single biggest clue, the strongest predictor for where a canyon will form, is just the steepness of the seafloor.
The continental slope itself.
Exactly. It's about tectonics shaping that sharp drop-off, not so much about the water flowing off the land.
Okay, let's unpack this then. Because my first thought is, what about something like the Hudson Canyon? It's sitting right off the Hudson River. That feels like more than a coincidence.
It is, but it's a different kind of connection than we thought. See, the steepness creates instability. Think of it like a sand pile that's just too steep. It naturally starts to slide.
So gravity's just pulling it apart.
Precisely. You get these underwater landslides, these slumps, and that starts to carve a little notch at the top of the slope. That's the beginning of the canyon.
So it's eating its way backward, upslope, from below.
That's the key. And then, once a canyon gets big enough to tap into the sediment being brought to the coast, either by river or just currents pushing sand along the shore.
Shore currents.
Right. Then it can really take off. It captures all that material and grows way faster than its neighbors. That's how you get the giants.
And when you say giants, you're not kidding. Some of these have walls that are, up to 5 kilometers high? The Great Bahama Canyon, for example.
Almost 3 miles, floor to rim. The force needed to carve that is immense, and it's not a gentle stream of water. The main eroders are these things called turbidity currents.
Which are?
Imagine a dense, fast-moving avalanche of sand and mud, all underwater. They could hit speeds of up to 70 kilometers per hour.
70? I mean, that's faster than city speed limits. An underwater avalanche moving at highway speed.
And that's how you carve out something like the Congo Canyon, which is just enormous. It stretches for 800 kilometers.
Wow.
And, studying these hidden processes, modeling features that are hundreds of kilometers long, completely hidden from view, it takes some incredibly sophisticated data analysis.
I would imagine.
It's all about predictive modeling, uncovering where specialized agents can make the most impact, whether for Earth system science or even for business automation, is just critical. Actually, if you're looking to accelerate that kind of work, AI, training, automation, software development, you should check out embersilk.com.
So bringing it back to the big picture, what does this all mean? Why should we care about these massive, hidden valleys?
Oh, they are absolutely vital for the global climate. They act like massive funnels.
Funnels for what?
For sediment, yes, but more importantly, for organic carbon, the remains of dead plants and animals. They shuttle it from the coast right down into the deep ocean.
So they're basically giant pipelines for burying carbon. That's huge for climate models.
Huge. We're talking somewhere between 60 and 90 million tons of carbon buried in the seafloor through these canyons every single year. It makes the deep ocean a critical carbon sink, and it regulates our planet's climate over geologic time.
And I guess on a more practical level, an underwater avalanche moving at 70 kilometers an hour is probably not great for, say, an internet cable.
It's a major hazard. These snap seafloor cables and pipelines all the time, so mapping them is essential for our infrastructure.
Okay, so here's a final thought for you to chew on. If steepness is the key, think about a place like the Mediterranean Sea during the Messinian Salinity Crisis.
When it completely dried up millions of years ago.
Exactly. The seafloor would have been a massive, incredibly steep basin exposed to the air. If steepness is the trigger, imagine the colossal canyons that must have been carved back then, now hidden thousands of feet below the waves, just waiting for us to fully map them.
A whole world of hidden geology.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.